Pessoal que está online, a gente vai dar início ao Meetup agora. Quem vai apresentar hoje aqui para a gente é o Michael, ele trabalha no time do Neo4j, e ele vai falar um pouquinho sobre modelagem, que é um tema que bastante gente pediu aí nos últimos Meetups, e a gente vai tentar trazer para vocês um pouco da experiência. Eu vou tentar fazer uma tradução simultânea, então quem tiver problema com inglês, eu vou tentar digitar quase tudo que o Michael falar no painel de texto. Vocês podem abrir, tem uma opção para abrir o texto aí. E no final vocês podem fazer perguntas. Também tem um aplicativozinho de QA que está habilitado, vocês podem mandar, pode dar um feedback por lá se vocês tiverem algum problema técnico. Acho que é isso, então. Michael, I think you can get started.
Hello, everyone. Good evening. So it's quite late in my place. It's already 11:45. So I hope you excuse that it's really dark here, even when I switch on the lights. But at least that you can see me and say hi. And now I'll disable the video to go to screen share. I want to talk about graph data modeling today. And in general, data modeling with a graph is a big topic, so I will not be able to cover everything here today. So if you have any more questions, don't hesitate to ask in the Q&A section or in our public Slack channel or on Twitter or in the Google group for Neo4j. And I hope you like the presentation. If you do, please tell your friends to also join the meetups. And support Hanneli in getting this running. So let's see, graph data modeling with Neo4j. Can you all see my screen, Hanneli?
Todo mundo consegue ver a tela aí? Eu acho que sim. Se alguém tiver problema, vai dar um grito no Twitter. I think so. You can go ahead.
Okay, cool. So first of all this content is not just for me. Many of my colleagues are also very interested in this topic. So Mark, Alistair, and Ian have worked a lot in the modeling space. I am actually involved in all parts of Neo4j. I've been with the company for more than 5 years now, and I do especially a lot in the Neo4j community and the Neo4j ecosystem. So all the people that build projects around Neo4j, drivers, libraries, and so on. I also work on the Spring integration for Neo4j, do a lot of performance stuff with Neo4j itself. Worked a bit on the Cypher language in the beginning, especially, and also a bit in the cloud efforts when we still invested into them. Today, I want to quickly recap the building blocks of a graph model, and also discuss, when talking about these building blocks, about certain aspects, how this relates to modeling. I quickly want to touch the NoSQL data models, because that's kind of important when you model with different kinds of databases. Want to look at a quick example, and then talk in detail about some of the patterns and anti-patterns that you have while modeling with graphs. In general, I think Hanneli already made this clear at previous meetups. There's a wide variety of use cases that you can use graphs with. So it's actually everywhere. So no matter where you look in the world around you, everything is connected. Every piece of information is connected with each other. People are connected with each other, to the company they work with, to the location where they live, to the people around them in their families, in their neighborhoods. But also in sciences, a lot of factors influence each other. In economics, markets are influenced by a lot of decisions and moves by companies, and so on and so on. So there's no piece of information actually in the real world that's disconnected from everything else. And that's why graphs are so well suited to model real world scenarios and real world use cases. And so if you look at data complexity, it's a function not only of size, which most NoSQL databases are built for, but also semi-structure, which means that you don't have a prescribed structure of your data, but as nowadays sources for data vary a lot, and many of those are also user-generated, you have oftentimes not the same amount of information about your entities as you had before, when you were still using forms a lot to generate data. And especially also connectedness. The more connected and related pieces of information are, the more complex the data is. Yeah, just to show you where you can see graphs. Of course, in social networks, as you know, if you looked at connections between people, friends, and sharing of information, but also looking for new colleagues or employees, or if you want to apply for a CV or so, then graphs are actually used in many of these places already a lot to find the right information. In impact analysis, it's also kind of obvious that if you have things that are dependent on each other and transitively so, then if you change one thing, that all the following or dependent things are affected by that. Of course, that's quite obvious in server setups. For instance, if I have a large network installation and I pull the plug somewhere, then all the things that hang onto this network are affected by that. But impact analysis is also important in lots of other areas. So be it in software, where you can analyze the impact of changes in your code or changes in libraries or dependencies, but also in other scenarios where you make business decisions and then these decisions impact other decisions and you want to use a graph to model that. Navigation, route finding, logistics, all of that is kind of impossible without graph algorithms. So shortest path algorithms and Dijkstra, A-star, and others are widely used to find your way from A to B. And that's both in the private sector, where we use maps and routing a lot, but also in the commercial sector, especially for logistics, parcel transportation, shipments, and so on. And flights, of course, as well. And for recommendations, this is not only kind of commercial recommendations like retail, but also if you want to recommend better music or books or people or events or locations to other people based on not just their preferences, but also their past behavior, the people that they are similar with, and also the content that's similar to the content that they already liked or disliked. So this is also an really interesting graph problem, and there's a lot of information and articles on that as well out there, where you can find more about this. In access control, which is one of the original reasons why Neo4j was developed, it's quite interesting that you can, with a really simple data model, you just have people groups which can be nested, and then permissions. You can build arbitrary complex structures, and resolving them in a relation database has always been a big pain, especially as these structures are variably deep. So you can have networks or trees that are 1 to 10 levels deep, and resolving these dynamic structures is really hard. And in the graph, it's just finding the shortest path between a resource and a person which has only permissions on the path, and then you can access the resource. So no matter where you, which way you went. So you see, there's a lot of areas where you can use graphs in the real world, and that's why I think it's really cool to just look at them and see where you can apply them. If you want to see some examples actually of how to use graphs with Neo4j, something that you can do is to go to graphgis.neo4j.com, and there are a number of use cases and actual real graph models and graph queries to show you how other people model their own domains with Neo4j. So the basic building blocks of the graph model, at least of the property graph model that Neo4j supports, is nodes, which are your entities or your pieces of information, relationships which connect these, properties on both nodes and relationships, and labels to group nodes into categories or into sets. If you look at a simple example here of people having purchased books and people having written books, if you look at the different aspects it is like this. So first of all, we have nodes. In our case, it's Ian and Alan and John Le Carre and Graham Greene as people, and then 2 books, Tinker, Tailor, Soldier, Spy, and Our Man in Havana, so which are kind of just entities with information. And in the graph, you can put any kind of properties on each node, so you're not restricted like in a relation database that you have only these columns that you can put there, but you can put arbitrary information on the nodes. So that means, in the first place, nodes are not really distinctive from the outside. Just when you look at the properties that they contain, you can kind of see the differences. And even for a single person, you can have just a single attribute like a name, and for the next person, you can have like name, biography, where they live, what they did, who their spouses are, where they work, and so on. So it's really depending on the amount of information that you have per entity, how much you want to store actually on your node. And every piece of information that you don't want to store that kind of is just default, you can just leave off and you don't have to store actually in your database. Between these nodes, you have relationships, which are directed connections from one node to another. And all these relationships have a name or a type. In this case, we have purchase relationships, we have wrote relationships, and you could imagine other relationships, like, for instance, fan of or read, like a person read a book. And in a graph database, these relationships can usually be navigated in both directions. So unlike an object model or relation database where you always have to create a relationship in both directions, you don't have to do that in a graph, only if you really want to and need to. But otherwise, you would only navigate the relationship in the other direction, or you would just ignore direction. The properties that you would put on a relationship are more qualifying properties. So you say, this relationship is active since a certain point of time, or this relationship has this weight, or this cost, or this rating. And so that's usually what you can put on relationships. Sometimes you also want to put other information on relationships. That's up to you. So you can have as many relationships as you want to between nodes. If you look at social networks, you can have as little as 0 to 1 million or more relationships on a single node. You can also have multiple relationships of the same type on a node. And you can have also arbitrary numbers of relationships between the same entities because there are more than one relationship between 2 people that you can have. And you can also have self-relationships, which is possible. And you actually use relationships to structure your information. So because if you put a node only on itself, then you can only say so much about it by looking at its properties. But if you put a node in context, or a piece of information in context to other pieces of information, you suddenly can say much more about this this piece of information. So for instance, if you know a person, then you know it's their name, perhaps their age, and so on. But if you know where they work, where they live, whom they're friends with, what they like to eat, what they like to see or read, or what they like to listen to, then you suddenly can say so much more about this person than before. And especially as this context is not just one step away, but you can also look at the second and third degree of these connections. So you don't just see a person, but for instance, also what their friends like, or what their location also has to offer, for instance, right? So you can derive much more from the place where you put a node in a graph. And of course, you can evolve that, so you can always add relationships to a node, like you would change data in another database. So if you would in a relation database, like change a cell in a table, the same way you can add relationships in a graph model. So it's not a schema operation or something like that, but it's really a data operation. Even if you create a relationship with a new name and direction, even that is just a data operation and not a schema operation. Having said that, graph databases in most cases are also schema-free, so you don't have to define a schema up front, but you can put some constraints in place which Neo4j supports some of which, and actually we're gonna add more of those in future versions, because many people that come from an enterprise background actually like to have more constraints in their data model, in the database. Perhaps not so much when they start developing, but if they get more towards production, then it's better to have more constraints in your model, because then you don't want to break accidentally things without knowing. And then the last thing, which I could have mentioned before, is labels. So initially we didn't have labels in the graph, which made it more difficult or cumbersome for people to represent types for nodes. And so there were various ways of representing types. But nowadays with labels, it makes it really easy. You just kind of tag a node with certain names. An interesting thing here is that you can not just put a single label on a node, like you would put in a class in an object model, but you can put any number of labels on a node. So you can say, okay, this is a book, but this is also an action book, or this is a person, but this person is also an author, or this person is also a employee, or this person is also a husband or a father, or this person is also a spouse or so. So, and depending on the labels that you have on a node, you can treat the different kinds of attributes and relationships as relevant for this label, which makes it really nice if you want to map this single entity in different contexts onto different kinds of representations. Okay. So to quickly talk about databases in general and NoSQL databases in particular. So we think NoSQL means not only SQL. So that means whatever database you need to do your job is the database you should choose for your project and system. And in many systems, it's not just a single database, but multiple databases, because each database is really good at something, and there are no databases that are equally good at everything. So because you always have to optimize for something. And so no matter if you look at document databases, key value stores, column databases, relational databases, or graph databases, each of them have their strengths and their weaknesses. And depending on what you want to do in your project, choosing one or more of them to solve a different kind of problems is the right way forward. Nowadays, many people build microservice architectures where they have different microservices use different databases, because the different services have to do different things. For a big distinction in this group of databases, I want to kind of quote Martin, who said that most of the NoSQL databases actually use an aggregate-oriented model. That means that their focus is on a single entity, which is identified by its primary key and a kind of more or less binary blob of data. The data can be more or less structured, like in a document database. But in general, you always access data by a key and retrieve the full or parts of the data. But this also means that any kind of operation you do on this data is only atomic within this aggregate. So when I want to change multiple entities kind of atomically, that's not possible in aggregate-oriented databases. So that's a kind of a shortcoming. If you have more complex business transactions, which change actually multiple entities and also connections between entities, then an aggregate store might end up with inconsistent data, or you have to deal with compensating operations your own to fix partially applied updates. In graph or connected data models, actually, it's different. So the connected data model or the graph data model is actually closer to the relational model, because you really have entities and connections to each other in the model. So you have a fine-grained data model, which is also more normalized than relational databases usually are, because it allows you to efficiently store these relationships. So where relational databases are not very efficient at storing relationships and querying them especially, graph databases are actually built for managing and storing relationships because what they actually do is they pre-materialize relationships. So whenever you query a graph database for a connection between two elements, it just has to retrieve the relationship. It doesn't have to compute a join between tables or indexes at runtime, but it only retrieves the already existing relationship information from memory, and then it's almost constant time operations to follow a relationship. And if you follow a number of relationships, then it's just linear time. So that's really nice in terms of performance, because you don't degrade as much as with traditional relational joins when you query graph models. The other aspect of the graph model that's quite important is that it's used for local search. So you wouldn't do as much of global operations, kind of aggregating over your whole million or billion element-sized data, but more, I have certain starting points. For instance, I have this person, I have this event, I have this location, and then starting from the starting point or starting points, I navigate out 1, 2, 3, 4, 5, 6, whatever steps out. And while doing that, I aggregate and filter data and then project my data at the end. So I always have kind of a local view on the data, which also makes it really nice to only load the data that's needed. So even if I had data about all the 7 billion people in the world in my graph database, actually querying this data is still very fast, because I only look at a certain subset of this data and not at all of it. So which makes it really efficient in terms of which data is actually active and which data is not active. Oh, and of course, graph databases are also transactional, because this fine-grained data model is needs actually a scope of updates. So whenever you want to update a fine-grained data model, and you have no kind of change scope, which kind of includes what kind of change is within my operation, and what of this is visible to the outside and not visible to the outside. And when I kind of finish my change operation, I want to make sure that all my changes apply, or none of it if it fails. This is actually a transaction, just a scope for changes. And for graph databases, that's an important aspect, because otherwise you would oftentimes end up with partially applied updates. Okay, if you compare the relation model with the graph model, many of you might have seen this already. So we have a relation model with tables, customer and account, and we have a join table in the middle. In this case here is customer account. Interestingly, many relational models initially start with a few tables, but as the data evolves and as the use cases evolve, more and more many-to-many relationships are added to the use cases. So the older a project gets, the more join tables actually are added to the project. So that means joins are getting more and more costly, because it's not just a connection between two tables that I have to resolve, but it's always 3 tables with 1 in the middle that I have to resolve. If I want to model this in a graph, it would look like this.
Oi, pessoal, eu acho que o Michael, ele deve ter perdido a conexão. Eu acho que daqui a pouco ele entra de novo. Desculpa aí o inconveniente.